Hello, I'm Jeong Woo Chang, and I would like to present EdgeChain on Edge-IoT framework and prototype based on blockchain and smart contracts. It is published in IEEE Internet of Things Journal in June 2019. Okay, here is the table of contents. I would like to start with the introduction with two IoT challenges, and then I would introduce the existing idea with centralized cloud model, and the authors newly suggest the edge chain as the suggested idea. And as the following contents, edge chain key approaches and designs would be described, and framework and functional modules, and also key processes and workflows would be described. And next, the prototype and evaluation would be described. And finally, I would conclude the presentation and with my short opinion. And here is the introduction. Internet of Things faces two significant challenges. One is scalability issue, and the next one is security issue. It is difficult to scale with massive number of devices in existing centralized cloud computing model. Why is that? Because there are so many data generated from devices, and in the existing centralized cloud computing model, there is so long distance between IoT devices and clouds. So it is really a big problem as the scalability issue. And the next issue is the security issue. Cheap IoT devices are with very limited security capabilities. It doesn't have any security software in uh, the IoT device. So, and also there would be the poor technical upgrading or maintenance services by the centralized cloud. So it faces largely these two kinds of problems. So how to solve these two challenges? So here is the existing idea with centralized cloud computing model. As you see in this figure, there are centralized clouds with high computational power in cloud tier, and there are many IoT devices in IoT devices tier with low computational power. Uh, IoT devices have no ability to compute any data that is generated by these devices. So the IoT devices offload data to the centralized cloud, so it delegates the tasks to the centralized cloud by allocating resources in these centralized clouds. However, as I mentioned in the previous slide, as IoT devices increases, there are so many data that should be created in the centralized cloud, so it has that kinds of scalability issue. And also, these IoT devices has no embedded security software, so it has also the security issues in this existing idea of centralized cloud computing model. So these are the problem in this centralized cloud computing model. So the authors newly suggest this idea of edge chain. In the existing model, there are only cloud tier, centralized cloud, and IoT devices tier IoT devices. However, they newly added the layer of edge tier in this figure. So this edge chain newly manages these IoT devices between the cloud tier and the IoT devices tier. So these edge nodes appends new block when the transaction newly creates. So these blocks just records all IoT activities from IoT devices and it is the means of secure data logging and auditing. So this new framework, this new edge chain just solves the two problems of scalability and security. Scalability is just solved with edge feature. This just close up the distance between resource provider in the cloud tier and IoT device in IoT devices tier by adding this edge tier layer. And it also solves the security issue with the chain feature because this blockchain just records every IoT activities and transactions from these IoT devices. So secure data logging and auditing is available by this chain feature in the edge chain. So these are the overall um, figure of the edge chain. And now I would like to explain the edge chain key approaches and designs. There are largely five key approaches. Firstly, it is consisted of permissioned blockchain. No every node creates block. This is not correct. Only Edge server is in charge of creating and appending new blocks to record IoT activities of devices. Those devices give transactions to the Edge server. Then Edge server collects every transactions from the IoT devices, and Edge server makes blocks for the blockchain and append blocks to the blockchain. Only Edge server does it. And the second approach is credit-based resource management. Each IoT device is created a blockchain account and given an initial amount of credit coins. So this credit coin balance determines the device's ability to obtain resources from the edge servers. So if the blockchain account has more balance, then the quicker and faster access of resource is available by this credit-based resource management. So every blockchain account has credit coin uh, in the blockchain. So this credit coin balance just determines the ability of receiving the resources from the edge server. And the next approach is resource-oriented smart contracts-based policy enforcement and IoT behavior regulating. So also in this framework, there would be no security software on IoT devices. Then how to guarantee the security of this framework? Just smart contract. Pre-program the resource policy in the smart contract. So every devices and every nodes in the blockchain would follow the rules in the smart contract by pre-programmed resource policy in smart contract. So EdgeChain regulates the behavior of IoT devices based on their resource usage and activities. So if the node X not good, then it would be blocked by the EdgeChain. So for example, if there is a compromised IoT device, then it would has out of balance uh, account and it would be put into the blank list by pre-programmed smart contract policy. And the next approach is evolutionary and backward compatible approach. Authors largely classify IoT devices into two groups, legacy device and non-legacy device. Legacy device is infeasible to run even the most lightweight blockchain client software, and non-legacy device just interacts with EdgeChain directly and requests resources to Edge server. This legacy device is the problem to the authors, so they just set even legacy device is acceptable in this EdgeChain framework by IoT proxy. this would be described in the later slides in more detail. And here is the final key approach of the edge chain. Um, it just supports standalone deployment and also distributed deployment. However, in the paper, only the standalone mode is described in detail, and distributed mode is just suggested idea. So standalone mode just suggests single edge chain box, so it can be deployed in smart home application, and in distributed mode, it just supports multiple edge chain boxes, so it can be applied in smart city application. In distributed mode, multiple boxes share the blockchain and the smart contract data. So this was suggested distributed mode. And in the paper just suggests the example of a standalone edge chain box deployment in smart home. So all the IoT devices just gives service request or data flow to the wireless router. Then this wireless router just routes these kinds of data flow to the EdgeChain platform. Then this EdgeChain platform just creates and monitors the data and allocates resources uh, for this service request. So here is the standalone mode. And if this wireless router just wants to communicate with the external network, then um, it should go through the firewall, and after filtering any service request or data flow, then it can communicate with the external network. So this firewall and external network is not related to this edge chain platform. Edge chain platform is really dependent to the security software, even with firewall. So this firewall and external network is just independent with this edge chain platform. So here are the edge chain framework and functional modules that is illustrated in this figure. So this edge resource provision is done by Edge Cloud, and these figures are all related to the blockchain module. And here are the IoT devices. So IoT devices is largely classified into legacy IoT devices and non-legacy IoT devices. Uh, these legacy IoT devices has no ability to install blockchain client, and non-legacy IoT devices has ability to install blockchain clients. So these non-legacy IoT devices just directly communicate with smart contracts. However, legacy IoT devices has no blockchain client, so it just communicates via IoT proxy to smart contract interface. So here are the large HTML framework, and I would like to describe these functional modules one by one. First, here is the IoT proxy. IoT proxy just listens and sniffs the legacy node's activities. So legacy devices are registered in the blockchain as non-legacy devices. So in the blockchain layer, the legacy devices and non-legacy IoT devices cannot be classified. It is just registered as non-legacy devices in blockchain, and also all activities of legacy devices are recorded in blockchain as non-legacy devices. So this IoT proxy is between the smart contract and legacy IoT devices. So legacy IoT devices can communicate with blockchain by this IoT proxy um, devices. And the next module is smart contracts interface. It has no special feature. Uh, Only special feature is that it uses Web3 protocol to create the smart contract instances for IoT devices. So these devices can communicate with smart contracts by this Web3 protocol. So it creates instance of smart contract. And the next module is smart contract. It supports two systems. One is digital currency system and the other is policy management. Smart contracts just possess the virtual coins to represent the trust levels of IoT devices. So the more trust levels of the IoT devices, the higher the virtual coin it has. And the next function is the policy management. It has predefined rules to analyze behavior of IoT devices, and also it has resource allocation policies in the smart contracts. And the next module is blockchain server. The blockchain server provides blockchain service where IoT devices connect to it as clients. So two functions are performed on the blockchain server. The first one is it executes the smart contracts by collecting the transactions among devices and generating new blocks. It is called mining process in this paper. And the second one is device information requests and activities are logged on blocks. So blockchain server, in other words, Edge server just executes these two functions and it is performed on the blockchain server. And the next module is application interface. Assume that resource requests are accepted by this blockchain server. Then this application interface opens the channels between smart contracts and the edge cloud to allocate the resource. So it supports the function using Node.js framework to listen to the events on the channels. And also it builds communications for IoT devices and edge cloud accordingly. Finally, this EdgeChain platform has the module of edge resource provisioning. Also, when resource requests are accepted, then individual virtual machines work as the basic units to meet the specific resource requests. So if there is any resource request, then this virtual machine is allocated to compute or uh, uh, has the role of memory, storage, networking, and intelligence work. These virtual machines just do these kinds of work that is offloaded by these IoT devices. So they are the provisioning resource types. So for example, if video stream based face recognition application uh, is the IoT application of this EdgeChain platform, then the Edge servers launch additional virtual machines in the server to process the video stream. Because non-legacy IoT devices do not have the power of processing this kind of video stream, Edge servers launch additional virtual machines to create this kind of offloaded task of the IoT devices. And here are the EdgeChain key processes and workflows. Um, it is largely consisted of 4 steps. Uh, Firstly, issue deploy blockchain, and next it deploys smart contracts, and the next step is registering device on blockchain, and the final step is IoT behavior regulation and activities management. These all steps are done sequentially, so um, it could be done, it could allocate the resource or regulates the behavior. This step from A to C is just bootstrapping a process of this edge chain, and this step D is the key process to regulate the IoT behavior and manage the activities. These IoT behavior regulation and activities management steps are largely consisted of these three steps. Firstly, it has IoT behavior regulation workflow and resource allocation based on pricing mechanism. And the final step is the behavior management based on credit system. So I would like to start with this deploying blockchain step. Here is the blockchain deployment workflow. Firstly, the blockchain client should be installed on the edge server, non-legacy devices, and IoT proxy. The installation should be firstly done in every blockchain node, and nextly, the configuration of Genesis block should be done. The configuration information consists of hash value block head, timestamp, and difficulty of block mining. This Genesis block configuration information just follows the Ethereum configuration information of Genesis block, so just refer to the Ethereum configuration when you want the detailed information of this Genesis block. And it initialize nodes and then create primary accounts of each node. Each node gets public key for unique identification. And the special thing is that it gets the inode address for each node. Inode address is kind of whitelist, so it is consisted of public keys, IP addresses, network ports of the edge servers, and some dependent IoT devices. So only these whitelist edge servers and IoT devices in this whitelist are guaranteed to handle in this communication of the blockchain. So after getting the inode address, it runs each client and blockchain syncing begins by adding this inode configuration to each node. And the next step is the development and deployment of smart contracts. First, the testing process should be done in the first part of the deployment of smart contracts. Because once deployment of smart contract is done, then any data uh, in the smart contract is initialized by deploying smart contracts on blockchain. So just writing smart contracts with given rules and write and run tests on running blockchain firstly. If the test passes, then the edge server deploys smart contracts on blockchain. So also these smart contracts are assigned with address and created as normal accounts on blockchain. And this address should be explicitly opened to every users in the blockchain. So when these contracts are ready to use, then users must have a copy of the correct address of smart contract to create the instance. This instance will be created with the smart contract APIs as you see in the functional modules of the EdgeChain. So note that the smart contracts specify various permissions to different devices. So uh, legacy device, non-legacy device, I mean non-legacy device and the edge server has different permissions to different devices. So all those devices has different functions and different functions are defined in these smart contracts. And the next one is device registration on blockchain. IoT device registration is largely classified into legacy device and non-legacy device. As I mentioned, legacy devices are just registered by this IoT proxy, and IoT proxy creates accounts for devices. It is kind of a delegated task. And otherwise, non-legacy device just register and create account itself. And after these kind of steps are done, they are adding attributes of devices to smart contracts. These are the registered device attribute, uh, and here are the device specifications. Uh, the device specifications with the star mark, it can be only updated by the Edge server, and other device specifications can be updated by devices. So account address, network port, input output data, bandwidth request, CPU request, memory request, storage request, and MAC address can be uh, defined by the legacy or non-legacy device. However, the from priority to last request ID attribute, it is only be updated by the Edge server, not the legacy or non-legacy devices. After adding the attributes of devices, then these devices are ready to listen to the IoT activities. And after register the IoT devices onto the blockchain, then IoT behavior regulation mechanism can be done by the whole EdgeChain framework. So this regulation mechanism is largely divided into legacy device and non-legacy device. Unfortunately, legacy device has no support of Edge Cloud to handle the additional workload. So this cannot allocate any resource on the Edge Cloud in the case of legacy device. The only thing with legacy device is just blockchain server monitoring. Blockchain server monitors its data flow to other IoT devices or outside network through a sniffer. This sniffer is kind of IoT proxy, as I mentioned. So smart contract analyzes the data flow and the behavior, and the smart contract compares this data flow behavior with the pre-registered attribute of the legacy device. If it is judged as the malicious behavior, then the blockchain blocks the monitoring of this legacy device. And if the behavior is judged as the normal behavior, then it keeps monitors the legacy device activities. What if the non-legacy device in the IoT behavior regulation mechanism? Uh, this device can request to obtain edge resource from edge server. Just smart contract analyzes the request and it also judges whether it is malicious or normal. If it is malicious, it's just lowering the credit points uh, of the non-legacy device and even block the IoT activities of the non-legacy device. However, if it is uh, judged as the normal request, then it just judges the availability of the resource in the edge cloud. If edge cloud has available resource, then it starts allocate resources to the non-legacy device. However, if the edge cloud has not enough resource toward the uh, resource request, then the resource request is rejected and logged in the blockchain. Then we should notify the resource allocation based on pricing mechanism. Through this scheme, the ordering of resource request and specific service resource allocation fee should be determined. Um, Resource has price, so price is changed through these three parameters. First one is current available edge resources, and the second one is requested edge resources, and the third one is application priority. This priority is largely classified into four levels of the priority based on the QoV mechanism. QoV of multiple applications and heterogeneous devices. So the first one is urgent monitoring. So it includes patient monitoring, people crowd sensing in the level 1 of the priority, and in the level 2 of priority, it is kinds of latency sensitive tasks. So virtual reality and augmented reality are included in these latency sensitive tasks. And the third one is reliable data transmission. Bank transactions and privacy transferring are included in this reliable data transmission priority. And the fourth priority is tolerant tasks. It includes light control, sensors based passive monitoring. So the lower priority it is more important. So the level 1 priority is the most important tasks, and the level 4 priority is not that significant tasks in this EdgeChain framework. Then how can the price of the resource can be determined? It can be explained in this resource allocation based on pricing mechanism. So the left one depicts the unit price of resource J for the request I, and the right calculation just shows the total price for request I. So this alpha and the beta is the constant value uh, for the price. So you don't have to uh, keep in matter of this constant value. Just uh, keep focuses on this Cj, Rij, and Li. Rij is requested resource J in request I, and Cj is current available resource J, and Li is priority level of request I. So as you see in this unit price, we can analyze two of things. The first one is the lower priority level, the lower price. So as I mentioned, if this priority level is low, then the task is very important. So the as priority level is low, the price becomes lower, as you can see in this calculation. And also the higher requested resource, the higher price. So the if this requested resource J in request I has high value, then this exponential term would be increases so that the unit price of the resource J for the request I would be increases. So the higher requested resource, the higher price. It is the analysis in terms of the price. So what if in the case of the request order, when the request resource J in request I is larger than the current available resource, then the request would be rejected. So it does not insert into the order queue, order request queue. Else, if the requested resource is lower than the current available resource, then the lower price, the earlier order of request. So as the price becomes lower, then the order of the request would be faster. And the next one is behavior management based on credit system. Uh, this is totally independent with pricing mechanism. It is just the incentive or punishment scheme for edge devices. The pricing mechanism was just the strategy for the resource allocation, but this credit system is just incentive or punishment scheme uh, for edge devices. It is kind of behavior regulation for these devices. So this credit system has large four features. Firstly, it has price threshold. So for every device, the threshold is set for a set. So if request price from the device I exceeds the threshold of the device I, then the credit is reduced. And the next one is that if there are too many requests from the IoT device, then the credit of the IoT device would be reduced. And the third one is network port. Uh, the IoT devices should communicate with specified edge server network port uh, as it is specified in a bootstrapping process. So if it does not communicate with predefined network port, then the credit would be reduced. And the final feature of the credit system is the data traffic target. So if the data flow destination is strange, then the device credit would be reduced. So these four features just determine the credit of the IoT device behavior. And now I would like to pass to the EdgeChain prototype. The left side depicts the edge server, so it is consisted of edge server cluster, and the right figure depicts the IoT proxy and devices. This desktop is just the IoT proxy, so it sniffs the data flow from the legacy device, and this laptop just monitors blockchain running on the edge server, so it is kind of means of monitoring. And here are the Raspberry Pis with cameras, microphone, and sense head. So these are the non-legacy device and the legacy device, which just consisted in the IoT device tier. And here are the access point, which just routes the edge devices with the IoT proxy. And here are the evaluation of the implementation. So it just starts with the storage of prerequisite software. Edge server just works as the full blockchain node, so it should have the function of storing every transactions of the blockchain, and also it should execute the smart contract software in the Edge server. So Edge server contains Ethash, Solidity, Truffle, Node modules, Node.js, and guest clients in the Edge server to work as a full blockchain node. Otherwise, IoT device just have the function of downloading the blockchain block, so it has only guest client in the IoT device. So IoT devices work as a light blockchain node, as you can see in the storage of prerequisites. And here are the figure for overhead of blockchain and smart contracts operation. Uh, because Edge server has more computing and bandwidth resource than IoT devices, so it has the higher throughput than the IoT devices in terms of Edge server. As you can see in the delay to synchronize a block and the figure for time to complete one transaction, the Edge server has higher throughput than IoT devices in terms of time. Uh, when you think of just computational resource usage for sending transactions, uh, it just has different percentage of usage as shown in this figure. Um, we can observe that the regular transactions has a very low percentage of CPU resource, while the memory usage is little higher since the CPU resource occupies 8% even in idle time. So it takes some memory overhead when you see this figure. And here is the overhead comparison with IoT applications. As you can see, the blockchain has lower CPU usage uh, related to face detection or natural language processing when you see this figure. However, also in memory usage, it has larger memory usage when it when it compares with other two IoT applications, such as face detection and natural language processing. So, in conclusion, it takes some memory usage when we use the blockchain feature. However, in terms of the CPU usage, uh, it doesn't matter because it has low CPU usage related to other IoT applications. So here is the conclusion. EdgeChain is Edge-IoT framework based on blockchain and smart contracts. But fatally, it has no support of resource allocation for legacy device with no blockchain software. The no support of resource allocation is really deficiency of this IoT framework. I think even device with no blockchain software should be supported with the resource allocation. So we should consider the way for data flooding for legacy device, which has no blockchain software inside. Thank you. Is there any questions for this presentation?